Hello everyone, welcome to the tutorial of GeneSys, an open source parameterizable NPU generator with full stack multi-target compilation stack, presented at the 56th IEEE ACM International Symposium on Microarchitecture 2023. Let me start by introducing the main project contributors. Hadi Ismailzadeh, Professor, Computer Science and Engineering Department, University of California, San Diego. Dr. Suruz Godrati, Systems Architect at Apple. Dr. Son Kinzer, Senior Software Engineer at Qualcomm. Myself, Rohan Mahapatra, a fourth-year PhD student in the Computer Science Department at UC San Diego. Han Yang, a third-year PhD student in the Computer Science Department at UC San Diego. Christopher Priebe, a second-year Computer Science PhD student at UC San Diego. And Lavanya Karthikeyan, who's currently a lead design engineer at Cadence Design Systems. Now, this research was in part funded by various agencies listed in this slide, and we would like to acknowledge their support. Let me go over the outline of the presentation. The tutorial consists of 5 sessions. The first session will provide an introduction of deep neural networks and the hardware acceleration and the various opportunities GeneSys provides for hardware acceleration. In the session 2, we'll talk about the template architecture of the neural processing unit that GeneSys generates and the FPGA prototyping. Now, these sessions also have hands-on instructions where people can use the AWS F1 FPGAs to parallelly do the examples. Third session will talk about our compiler, which we call the codelets compiler, and also the programming model. In the fourth session, we'll show how we can do quick design space analysis using GeneSys and perform the various performance analysis using GeneSys. And finally, we'll conclude and talk a little bit about the future work. So the key takeaway for the participants is they'll learn how to use and leverage GeneSys, a platform that can generate hardware accelerators for deep neural networks. The participants will also learn how to accelerate DNNs on an FPGA and prototype the neural processing unit generated using GeneSys on an FPGA. The participants will learn about a deep learning compilation framework and how it can be used to automatically translate DNN models written in PyTorch or Onyx models into a set of codelets that can be mapped into the hardware engines of the neural processing unit. The participants will also gain insights into the acceleration trade-offs and impacts on performance for various different deep neural network models and for various different configurations of the neural processing unit. And finally, we'll also talk a little bit about the system research opportunities that were enabled for us using GeneSys, and the participants can also use GeneSys to perform various different types of research. And I will start by talking about the various research opportunities that are possible and that GeneSys can be used to explore. So deep neural networks are powerful machine learning models that can learn from large amount of data and perform complex tasks such as image recognition, natural language processing, and even reinforcement learning. One of the most prominent applications of deep neural networks is autonomous driving, where DNNs can enable vehicles to perceive their surrounding, for instance, detect the objects in the surrounding, plan the routes, control the action of the vehicles, for instance, turning or stopping the vehicle without any human intervention. Another very common application of deep neural networks is the conversational chatbots, for instance, ChatGPT, where deep neural networks can generate natural and engaging responses to human queries and requests using natural language understanding and generation. A third application of deep neural networks is neuromodulation, where DNNs alongside other DSP or digital signal processing kernels can help design and optimize devices that can stimulate or inhibit neural activity for treating neurological disorders such as epilepsy, Parkinson's disease, and depression. Now, these DNNs, as I told, some of them are executed on the data centers and some on the edge. But talking about the hardware that executes this DNNs in the data center and edge, these hardwares have very different requirements today. Let me first tell about the hardware that is used in the data centers. As shown in the slide, these high-end domain-specific accelerators, for instance, the GPUs by NVIDIA or AMD, is Tensor Processing Unit by Google. There are a lot of different ASICs manufactured by various companies. In the slide, you can see GraphCore ASIC, and then finally there are a lot of high-end data center FPGAs. For instance, the AMD Xilinx Alveo U250 or U280, FPGAs. These accelerators provide a lot of compute throughput. For instance, as shown in the slide, on the x-axis, you see the parameter of deep neural network in millions. The y-axis plots the gigaflops that the deep neural network model requires, right? And on the bottom left corner, you see that the previous models of DNNs such as MobileNet or EfficientNet had significantly less number of parameters and demanded lesser amount of compute throughput in terms of gigaflops. But as deep neural networks have emerged and they are becoming more and more complex and larger, for instance, on the top right you see GPT-3, which demands significant amount of gigaflops and has a lot of parameters. Specifically, the largest model has 175 billion parameters. In fact, today the state-of-the-art hardware accelerators or domain-specific accelerators, such as the NVIDIA H100 GPUs, which offer almost 80 GB of memory per GPU, are not even capable of hosting a single GPT-3 model. And that's why what people have done is they have scaled out the model. Scaled out the inference of these newer emerging DNNs into multiple different compute units. And now data centers, as shown in the slide, are going towards a disaggregation where the storage nodes are separate from the compute nodes. Now, how do you scale out the model? How do you place the model in different compute units? Where do you store the data? Where do you store how do you leverage the memory such that the models are the inference is not memory bound? Are some of the kind of like interesting research questions. And to specifically talk about the various research opportunities that lie in just scaling out a DNN model. And this is just a specific example. There are many other, problems that people can explore. But just to scale out, people can work at the application layer where how do they do the parallelization of the model? For instance, how do they do the how do they should they use data parallel or model parallel or pipeline parallelism to distribute the model across different devices? Or for instance, in the compilation layer, how do they perform graph level optimizations? Or for instance, how do they perform scheduling such that the compiler can efficiently map these different kernels into the hardware? At the system, system and the networking layer, how these different devices should be connected. For instance, what should be the topology or how the congestion control should work. These are very interesting research questions that people can explore, and GeneSys actually provides a way for people to explore these, and we'll come into how GeneSys can be used. Now then, at the other end of the spectrum is edge computing, which also uses a lot of accelerators as shown in the slide for efficient execution of deep neural networks. However, these domain-specific accelerators have a completely different, constraints compared to the data center accelerators that we discussed previously. Specifically, these accelerators as shown on the left bottom corner demand a very strict power limitation because edge devices generally operate under on a battery which has a strict, and therefore they have a strict power requirement. Now, to reduce the power of a accelerator, there are various different techniques. Specifically at the architecture layer, how do you design? How do you design the architecture, the microarchitecture? For instance, how do you implement clock gating or power gating, where you don't power on a specific module in the hardware if it is not in use? Or for instance, how do you do dynamic voltage frequency scaling, DVFS, depending on how the load is, right? Or for instance, how do you do like signal routing or floor planning such that you can reduce the data movement or the length of the wire that connects from one module to the other module to save power? These are a lot of there's a lot of opportunity for architecture and microarchitecture research, and GeneSys can come in and people can change the architecture of GeneSys to perform research in these areas.